Everybody, would like to discuss today the I/O operations of the ATMEGA 328. Before starting with discussing ports and how we can get inputs inside the microcontroller, which is in our case the ATMEGA 328, we need to discuss a little bit the number of pins it has. So the ATMEGA 328 has 28 pins. From these 28 pins, we make use of 3 ports for input and output usage. These ports are port B, port C, and port D. Port B will be 8 pins. Port C has 7 pins only, although the GPR and the IOs are 8 bits, so we have one unused bit here. And in port D we have also 8 pins. Okay, so the locations of these bits, we have port C starting from bit 23. This is port C. Also here we have VC6, the 7th bit, and we have port B also here, port B, and port D this is, and here we have port B. Okay, we also have some bits here for port B, and here some bits for port D also. Here we have some bits for port B and for port D. You can check out the data sheet for the ATMEGA 328 to check exactly where each port resides. So now, to control these ports, we have 3 I/O registers for each port. So for each port, we have 3 I/O registers. These I/O registers are PORTx and PINx and DDRx. So where X will be port A, B, C, or D, and port is used for output data. Pin is used for input data, and DDRx is used for actually choosing if we want input or output. So what do we mean by all of this? So assume we have port B. So port B, we have, for port B, we have DDRB, pin B, and port B. For port C, and by port we mean just the pins on the microcontroller, we have DDRC, pin C, and port C. And for port D, the same is occurring. We have DDRD, pin D, and port D. These are all I/O registers. So if I want to look at the I/O, so let's say this is the RAM. We have here the GPR, And the I/O part, we have pin D, pin B here, for example. We have DDRb, and we have port B. Of course, we have the SRAM, and we have the rest of the port C's and port D down there. The address will be here. Well, the I/O 23 0x24 0x25. Of course, these are the addresses of the I/O register for pin B. So as we said, DDRb, so let's take the case of port B. DDRb selects if input or output. So what do you mean by this? Is port B going to act as an input or as an output? So in this case, if DDRb is 1, implies it serves as an output. If it's 0, implies this serves as an input. So let's focus on this part. So assume we have this microcontroller. So this is the ATMEGA 328, and we say that this is port B. I'm not going to be accurate about the placement of the pins, so assume we have here PB0 till PB7. So these are the 8 pins. So 1, 2, 3, 4, 5, 6, 7, and this is the 8. So from PB0 to PB7. Okay, these are the actual pins. So now we have DDRb. So this is DDRb. Okay. So of course it has It has 8 bits since it's in the I/O. Okay, and let's say we have, okay, this is another register called port B, which is the output, and it has also 8 bits, and we have pin B, which also has 8 bits. So what does all this means? So if we have 1 here, this means PB0 is output. So this pin acts as an output. So in this case, I need to check this out. Okay, so now I can read values from port B. However, if I have this placed as an input, I need the second bit to be placed as input. I place 0 here, and this means I need to check this bit. Okay, so we can select which pins are input and which pins are output. So what do you mean by input and output in this case? So this is the microcontroller. Okay, again, so if I want as an output, I can have some, I don't know, an LCD. So in this case, port B is output. On another case, if I have a sensor, and this is the microcontroller, in this case, port B is input. And in the first case, I have data being outputted. This is data outputted or placed on port B. In this case, data is read from pin B. So in this case, we have data coming like this. The sensor is placing data on pin B, which I can read, and in the first case, data is placed on port B. So this pin can serve as an input or as an output, the way we want it, depending on the value of DDRB. Okay, if there's a 1 in DDRB, then this is an output, and I read and I place data on port B. And if the bit 1 or PB1 in this case, let me write this, PB1 is input, and I read value from here. So if I have this is if this is 1, this means the red value is 1. However, if I want to work with port B and they say this is 1, then this is placed on the pin. This is read from the pin. So let me play this. This is read and this is placed. That is on the specific pin. So we have the ability to configure each pin to be an input or an output. If it's an output, we place values on port B. If it's an input, we read values from pin B. So this is the distinction between the two, and we're gonna take examples. First, we're gonna take examples by setting the whole port as input and output, and then we configure accordingly. So let's take the example of placing value on port B. So configuring port can be C or D, just change the letter, but we're gonna take port B to avoid confusion as output. So what we want to do here is just toggle port B infinite times. So what we have here, let's say, imagine we have some LEDs, and this is the microcontroller. We have some LEDs. So on all the pins, and you want to toggle them. So first of all, I'm gonna place some value over on port B. So initially, whenever we're dealing with problems that deals with I/O, we need to configure what do we have here. Since I'm placing data onto the port, this means we need to output data. So what shall DDRB be? In this case, we need to use out. Remember, DDRB is a I/O register, and we're gonna configure all bits as output. So here, all pins of port B are output. So I can place the whole 8-bit value. So now this what configured the port as output. So if I want to place a red box over it, because this is the main point, this is what we added here. So this configured the port as output. Now I'm gonna do my loop, and I'm gonna again place 16 over place FF over R16. Now placing over port B, So in this case, what I'm doing is saying port B will be equal 0xFF. This means all here will be ones. So all the LEDs will be turned on. Now, let's say I have a function called delay, just so I can see the difference with the LEDs being switched on and off. I can go ahead and say, okay, I can complement R16 and then out port B R16. In this case, I turn it off. So all the LEDs will be off. Call delay again. And then I say R jump L1, where I will have somewhere a delay function. Let's say this is delay for 100 milliseconds. Okay, so the main point here, we were able to place data on port B because we configured it as an output. Otherwise, we will not be able to place any data. And in this case, we placed the whole port, all the pins here as output, because I don't need to configure each bit by itself. I don't have one bit as an input, one bit as an output. I have all the bits as output, and this is why we placed FF on DDRB. Now, for the case of an input, let's take an example for the case of an input. So here configuring port B as input. So in this case, we just assume that we have, this is the microcontroller, and let's use another port. Let's use port C. So let's say assume port C is here, and we have some sort of a sensor, and this sensor is just giving data, and I want to place the data on port B. So this is port B. Let's say I have here a display. So if I want to write this problem, I want to read values from a sensor and placing it on the display connected to port B. So assume a sensor is connected to port C and a display to port B. Write a program that displays the value of the sensor on the display. So in this problem, I wanted to know what is the output, who is the output, and who is the input. So in this case, port C will be input and port B should be set as output. Since I'm displaying value, I'm outputting value to the display. And for port C, I'm inputting data from the sensor. So data is coming from this place, and then I want data to go out from port B. Okay, so in this case, first I need to configure the outputs and inputs. So the first step is, when looking at this problem, I need to set up my ports. So let us set up ports. So in this case, I'm gonna start with port B. So I'm gonna say LDI R16 0xFF, and of course out DDRB R16. This sets port B as output. Now I want to set port C as input. So I need to clear it, and then I'm going to place on DDRC R16. So here port C is input. Here port B is set as output. So you see the importance of these two. Then I'm going to continue here. So I'm going to do my infinite loop. So first of all, I need to read the value from port C. So the way to read value, I use N, and I'm going to place them in, let's say, R17. Come on. This will be read from port C. And now, what I want to is, I'm going to output, let's say, I'm going to call some delay, just to give the time for the sensor to work. And then I'm going to say out to port B what I read from port C. Excuse me, this is not port C. This is actually common mistake. I need to always, this is pin C. Okay, when we read values, we always use pin C. Okay, so this is not port C, this is pin C. And when we want to read something from a port, we use the pin. When we want to output values to a port, we use the port B. So whatever the value is in pin C will be placed in R17. We call the delay, and then we output that value into port B. And then let's say we call a delay again to give time for the port to display the value, and R jump L1. So the main thing that we want to check here is that this is setting all my inputs and outputs. Here the whole port, all bits in DDRB is 1. This means all pins are output. All pins in DDRC are 0. This means the whole port is input. Now to read values from the port, I use the instruction N, because I'm dealing with an IO register, pin C, and it gets whatever value there is into R17. I call the delay, and then from R17 I place the value in port B, and in this case I use out with port B and in with pin C, and I loop forever again. So as I said before, we have the ability to configure bits to be our pins in a port to be input or output. So pins of ports can be individually configured as output or input. For this, it's very convenient to have bit level instructions. So instructions that work on a bit level. So let's say I want to set a specific bit in a IO register. So let's say I want to configure, let's take an example, configure, let's say pin PC6 as output. What do you mean by PC6? This is port C, pin 6. So what I do is I need to set this specific bit. I can use a mask, or I can use the value directly and load it inside of PC6 and DDRC. So what I can do is something like LDI, and I'm gonna say R16, comma, let's work with the binary, and we have, so this is bit 7, this is bit 6, and then all of them are zeros. and then what I do is I place this value in DDRB. I'm gonna use out DDR, C R16. So we can do something like this. This is pin 6. Remember, this is pin 0. Okay, so another way to do it is with an instruction called SBI, and it takes an IO register and a bit. So in this case, the IO register can be any of the ports or any IO register, and the bit is the number. So I can replace these two by saying, okay, SBI DDRC, 6. These two are equivalent. Okay, so if I want to place, let's say if I want to do an input, let's say configure pin 3 of port B as input. So all I can do is use the instruction CBI, which is clear bit IO register comma bit, and I can say okay, CBI DDRB comma 3, and this clears pin number 3 or bit number 3. Remember, so what we'll have in DDRB, this is 0, 1, 2, 3, and we'll have 0. So this will be, if you want, pin number 3 or the 4th bit, because we start from 0. So this a little bit can be confusing. Is it the 4th bit or the 4th pin? It depends. So pin number here, pin number 3. Okay, so if I look at the IOs, this is pin number 0, and this is pin number 3. Okay, now if I look at the binary representation of SBI, so SBI takes an IO register and a bit number. So if we take, this is A and this is B, so A can take values from 0 to 31, all the IO registers, and B can take values, of course, from 0 to 7, because B can only can take values bit 0, bit 1 till bit 7. So if I look at its binary representation, 1001 is the opcode along with 1010, and then we have 2, 3, 4 and A, and we have 3 B's. So for example, if I have SPI port B, 3, I need to check what's the value of port B in terms of address to know exactly what to place in the A's. So if I want to translate this to binary, of course this stays fixed. Now if I check what is port B, okay, in this case port B has the address of 25. So this address, if I look at the data sheet, this has 25. Is that port B is 0x25. However, this is the true address. If you look at, this is the IO memory, then we have somewhere, this is port B, course this is the address, will be 0x25, and the relative address, the IO address, will be 0x05. As you know, to go from true address to IO address, what we need to do is subtract from 0x25, we need to subtract 0x to 0, and we will have 0x05. And what is 0x to 0? It is we subtract 32, which is the difference between the relative address and the IO, the true address and the IO address. So if we start here, this is 0x20, and this will be 0x00. Okay, and this is the first IO address. So instead of placing 25, which is of course more than 5 bits, we're gonna place 05. So let's place it in a different color. So we have here 0, okay, 0, 1, 0, and this is 1. So this is the 5 that is placed here, and then we're gonna place the number of bits. So here we want bit 3, so this will be 0, 1, 1, and this is what the number of bits that we have. So let's take another example with another register, and this time we're gonna use CBI. So the case for CBI is similar to the case for SBI, and let's take, so CBI, it takes the IO register and bit number. So let's take, in our case, we're gonna take a say CBI, let's say DDRc, comma, let's say pin 7. Okay, so if we want to check what is DDRc, we look for the data sheet, and we notice that DDRc has a true address of 27, and of course the IO address 0x27 will be 0x27 minus 0x20, which will be equal to 0x07. So now we check the layout of CBI, and in this case it's going to be 1001 and 1000. Now we place 1, 2, 3, 4 A and 3 B's. So now if you want to place the value again, and this time for the case of DDRc, 7, so we have 1001. This is the opcode, of course. Now first we place the A's. In this case the A's will be equal to 7, so we have 0, 0, 1, 1, 1, and also here we have 7 for the B's. We write 3 ones. So as we said, this is the bit number B equals 7, and this is A equals 7 again, and this A is coming from here. So this is how we transform the binary values for CBI and SBI. Two more useful instructions are for testing. So we're gonna take another 2-bit level instructions. So in this case, let me start on a new paper. It's better. We have instruction for testing bits. We have SBIC, takes an IO register and a bit number. So we can do something like, so what is SBIC? So skip next instruction, skip next instruction if IO bit is clear. So what do we mean by this instruction? So usually SBIC, we want to check if some bits are on or off. So usually we use them with pin. For example, I can use with SBIC. So I say SBIC pin B, comma 0. So what I'm saying here, I'm saying if pin B dot 0, okay, equal 0, then skip next instruction. Okay, so what do we mean by this? This is, I'm gonna skip this instruction. I say here jump pin B set. Okay, and here we'll have pin B clear, and somewhere we'll have PB set to do some stuff. Okay, so if pin B equal 0, we skip the next instruction. Okay, otherwise, else continue. So if pin B is 0, so I'm gonna skip. So this will be if true. Otherwise, this will be else false. Okay, and of course I have the alternative for this, which is SBIC. So if I check SBIS, in this case, IO register, come on, the bit number. So skip next instruction if IO bit equal 1. So in this case, I can do something like this: SBIS. Let's say, of course, pin B, comma 3, and if it's true, I'm gonna skip. So otherwise, so this is true, this is false. So in this case, I'm gonna jump to PB 3 clear. In this case, if it's true, I'm gonna skip this instruction and I'm gonna go to PB3 set, do whatever I want, and somewhere will be PB3 clear, and here I'm doing the if else again. Okay, so with SBIC and SBIS, I can do some setting and resetting based on a condition. So let's take an example on a doorbell. Assume we have a switch, say this is a switch connected to PB3, and we have a buzzer connected to PC5. So now if PB3 equals 0, this switch closes. Remember, this is an active low switch. PB3 is always going to 5 volt unless we pull it down by closing the switch. So once we close that switch, this buzzer will turn on and we will have a sound. So as with all I/O problems, first we're gonna start with setting up I/Os. So in this case, the switch is an input and the buzzer is an output. So we're going to use CBI. Here we are clearing, so we need to configure pin B, in this case DDRb, comma 3 as input, and we're gonna set pin C5, which is DDRc, as output. So here we finish connecting the configuring the inputs and outputs. Now what I want to do is test input. So I want to see if PB3 goes to 0, then I'm gonna turn on the light, the buzzer. So what I do is I'm gonna do a loop that does not get out unless this goes to 0. So I'm gonna do skip if clear for pin B, comma 3. So this, if I go, if this is clear, this means somebody closed the switch and I'm clear. Otherwise, I'm gonna go here. So this will go forever unless somebody presses the button. So loop forever unless PB3 equal 0. So keep on going. Once somebody closes the switch, I'm off the loop, and here I can say, okay, I'm gonna set, in this case, port C, comma 5. I'm gonna turn on the buzzer. This is turn on buzzer in this step, and I'm gonna exit. Sorry. Say this is exit, R jump, exit. So I'm gonna be placing here. So this is a small problem that it will keep on testing unless we have a clear value. So let's take another example where, let's say we have two cases. If we have 0, we need to do something, and 1, we need to do something else. So let's say we have a switch connected to PB2. So if switch equals 0, send the ASCII Y to port D. If SW equal 1, which is, this is the switch, send the ASCII N to port P. So we assume here we have an LCD that displays Y and no. So in this case, of course, PB2 will be input, and port D, this is port D, and port D will, all of it will be output. So for this problem, let's say if I want to draw it, I have the switch here. So this will be a active high switch. If I want, if it's well, it's also okay. I can do it like this again, or use an active low switch. And here we have at port D, we have an LCD. This is port D. So first I need to configure the output, configure IOs. So here PB2 is input, so in this case I'm gonna clear it, DDRb, comma 2. This will be output, so I cannot use CBI and SBI because the whole thing is output. So I'm gonna use LDI R16 0xFF and out DDRc as R16. So here all the port is set as an output. After configuring the IOs, I need to start my loop by testing. If it's equal to 1, then I'm gonna place N on port D. So what I'm doing is we're gonna go ahead and say, again, what I want to do is I'm gonna test if it is set for my switch, which is at pin B. Remember, pin B is input, so this is why we're using the pin mode, not the port mode. So if it is set, I will skip this instruction. Otherwise, I'm gonna go to, let's say, PB2 clear. This is my label. So here, I'm gonna skip it if it's true. This means somebody pressed it to 0, and I'm gonna place, so if this is 0, okay, if this is 0, I'm gonna send Y, right? So if I close this switch here, this will be brought to 0, and I need to place Y over this fact. However, if it's still 1, this means I need to send no to the port D. So I'm going to say LDI R16, okay, and here when we want to send ASCII, we don't have to write the equivalent binary. We can just say N with single quotes, and what we can do is we can output it on port D. Otherwise, okay, and here we can just go ahead and repeat again. So we will keep on doing this forever. Otherwise, this part, we're gonna go to PB2, clear, this is my label, and I'm gonna say, okay, now I know that this was not pressed, it was not closed. I'm gonna say, okay, I'm gonna send yes, and out port D, R16, and R jump again. Okay, so this case, so this is the case where SW equal 1, and this is the case for the switch equal to 0. So you see how we are having here if and an else. Okay, and you remember always, whenever you finish the true, you cannot continue to PB2. You need to go again or actually exit the code. Okay, with those instructions, with CPI and SBI, we can create a PWM signal or a signal that has a square wave. So let's talk about creating square signals also. So let's say I have a microcontroller that I want to create a square signal with a duty cycle. So write a program that creates a square signal on port C bit 0. So usually we have, when we say square signal, this means this is equal to this. So if you call this T on and this T off, okay, the duty cycle is equal T on over T on plus T off. So in case of a square signal, this means 50% duty cycle or half. So this means T on equal 1 and T off is equal 1. So to do this, we're gonna write the following program. So first of all, since I'm using a delay, and a call instruction, I'm gonna start with configuring my stack pointer. So I'm gonna start with, and then out SPH R20. Then I'm gonna do LDI. You can use the same register, it's fine. RAM end here. If you don't know what I'm doing here, review the previous lecture where we discuss the stack pointer and how we can load the stack pointer in order to call some functions. So here what I'm doing is initializing the stack pointer. Now, so first of all, I need to configure my I/O pins. So here, configure I/O pins. So I have just a single output pin, because what I'm trying to do is generate a square wave. So first of all, I will do SBI DDRc, 0, because we're working on PC0. And then I need to create now an infinite loop, and in this loop I'm gonna first set port C, 0, call a delay, then I'm gonna clear port C, 0, and then call the delay, and we're gonna jump, we can use our jump here. So here what we're trying to do is the following. So we start with this instruction. So first, this instruction SBI port C is just, let's say this is port C. So it is started with port C equal 1. So this is equal 1. Then I call the delay. So this will stay until delay finishes. Of course, when we call delay, there will be a function here, delay, that performs the delay operation. Again, this will be in the previous lecture. How do we create delays? So with port C now, we create a delay. This, let's say, equal, for example, 10 milliseconds, whatever the value is, and then we clear it. So after the delay finishes, this is cleared, then we wait for another delay, and then we go up. We neglect the overhead for our jump and the execution of the instructions, it's very small, and then we set it again, go like this, and then go like this forever. So all of this is delay. So with half, so this is T on, this is T off. So if we take this value, this will be T on over T on plus T off will be equal to half. Now if you want to change the problem to have 66% duty cycle, so let's say I want to do a 66% duty cycle. This will be roughly, if we look, 2/3, right? So this means duty cycle is equal to 2/3, implies T on over T on plus T off. This means T on will be 2 and T off will be 1. So if I want to modify this problem to have double this duty cycle, or to have, sorry, 66% duty cycle, this means I need 2 places delay. So this means what I want to do is actually this is delay and another delay, 1 delay for off and then 2, and so forth. So this is the effect I need to do. So if I rewrite the loop, so of course I'm going to start with SBI port C, 0. I call delay 1 time, I call delay another time, and then clear port C, 0, and call delay just 1 time, and R jump here. So in this case I have this effect: 1 delay, 2 delay, off, just 1 delay, 1 delay, 2 delay, off, and so forth. Okay, so we have twice as much on as off, and this is the way we do it with just adding a single delay. And this will finalizes our lecture for I/O ports.